Hi folks, welcome to Captain Rod's Introduction to Principles in Work and Energy. So the purpose of this video, as kind of mentioned in the beginning here, is to give you an idea of what energy concepts are, and later on in other videos I'm going to kind of put them together and attach some mathematics to them. But for right now, what I'd like you to imagine here, I got three scenarios to imagine. Scenario one here, a person lifts a rock up. Scenario two, a car is accelerating down the road. So in example 2, I want you to imagine that the car is actually speeding up 20 mile per hour, 30 mile per hour, 40 mile per hour. Example 3 is a person is making a smoothie or something over here. So this is a blender, and they're blending up their favorite stuff here, yum, for their smoothie. So in all three of these examples, it's very important to take note that work is being done. Okay, so the person lifting a rock, remember, work is force times distance. The person is applying a force in this direction on the rock when not only when it's sitting stationary, but that force is required to lift the rock. When the car is accelerating, it takes a force applied to the car to accelerate it down the road, and that force is applied at the rear tire if it's a rear-wheel drive car, or at the front tire if it's a front-wheel drive car, right? And the motor is what basically produces that force. And then in the case of the blender, I have to kind of blow this up, but we've got ice cubes and stuff in here, and then these blades spinning round and round, chopping things up. The blades are applying forces to the pieces in there, right? So in all three of these cases, there's work being done. Or actually, to go back to the blender example, the shaft of the motor has to be turned, and forces have to be applied to turn the shaft of the motor. And when the shaft turns, there's work being done. So what you have to realize is in all three cases, there is work being done. All right. Another thing that you have to realize is that, let's talk about what's doing the work. In example 1, it's the person doing the work, applying the force to the rock and moving it. In example 2, it's really the motor of the car doing work. The motor turns the drive shaft, which makes the tires turn, which creates that force there. And in example 3, it's the electric motor in the blender doing work. Now, another really important thing to realize is that in every one of these systems, the thing doing the work has to have some sort of intrinsic input, I guess, so to speak. So, for example, the person here. The person has to eat food. If they quit eating food, eventually they will lose their ability to lift the rock. In fact, if they don't eat food, eventually they will become room temperature and not be able to lift anything. In this example, the intrinsic thing that has to be put into the system here is gasoline, right? If no gas is put into that vehicle, eventually it will run out of gas and not be able to accelerate down the road. And third, the blender example has to be plugged in. It has to have some sort of electricity source. So all three of these systems have to have some intrinsic input here. And that's hinged to a concept called energy. And here's how energy is defined. All right, energy is defined as ability to do work. So in the person example, the person eats food. The food carries with it an energy. That gives the person ultimately the ability to do work, lift this rock, move down the road, mow your lawn, etc. In this example, the gasoline at the molecular level basically has energy stored within it. That energy gets released, giving the automobile the ability to accelerate down the road. And in this example, this is, I guess for now I'll just say an electrical energy input. This energy is coming from, ultimately, a power company. It's usually coming from the combustion of fossil fuels or maybe nuclear or something like that. All right, so the details of this, not super important for right now, but all three of these examples require some sort of energy input. And energy is what gives a system the ability to do work. Energy comes in two types. There's what's called potential energy. And I like to define potential energy like this. Potential energy is defined as energy due to position. And then there's what's called kinetic energy. And I like to define it like this. Kinetic energy is defined as energy due to motion. All right. So what I'm going to do here is I'm going to stop this for a minute, clean my pictures up, and talk about potential and kinetic energy in a little bit more detail. Hi folks, all right, so I'm back. I've kind of drawn another picture here, and you know what I want you to imagine is this. This peculiar looking thing here is an anvil, all right? So think about back in the old days, you know, an anvil essentially is just a giant chunk of metal. So it's a big, big, heavy object. And here's a person standing here holding up the anvil. And imagine the person's goal here is to drive this into the ground. This is just some sort of stake. And in this example, their method of driving it into the ground is this. They just release the anvil from rest, from the position shown. The anvil will accelerate down, hit the stake, and then presumably it will apply a force and drive it into the ground. So what you have to imagine here is this anvil in this position, I'm going to call this position 1. This has a potential energy because the potential energy is defined as energy due to position. The system, now technically the system is the anvil-earth combination, and we'll talk more about how systems are defined later, but for now the important thing is that the position of the anvil, combined with the fact that there's gravity in this example, gives this system the ability to drive this stake in. When the anvil is dropped, it's going to accelerate down. When it hits the stake, it will apply a force in this direction, and then presumably the stake will move to some sort of new position, right? It's going to move some sort of distance there. So when it does so, work is done. Force times distance. So this system has an energy, and that energy depends on how high the anvil is. So there's the position dependence of it. The higher the anvil is above the stake, the higher the potential energy. So that's one example of a potential energy. Here's another example. A person maybe has a bow. Right, and this person wants to fire an arrow here. So in order to fire the arrow, what they're going to have to do is draw back the bow. When they do so, they have to do work, because they have to apply a force to the string, and they have to pull, and the string moves. So what will happen, I'm going to draw the picture with the bow drawn back now. When the bow gets drawn back, right, and here's the person holding it. And again, I'm not much of an artist, but in the drawn back position, the position of the bow and arrow and string all together now has an energy associated with it. When this person releases this system, a force is applied to the arrow in this direction. The arrow starts moving some sort of distance here, and work is being done. So work will be done on the arrow. So this system right here has a potential energy based on the position of the string and the bow. So those are two pretty common examples of potential energy. There's more that I'll talk about in other videos, but for now, that's enough on potential energy. I want to talk a little bit about kinetic energy. So I'm going to pause this again and draw another picture. All right, folks, so I'm back here, and we're going to talk a little bit now, a little more about energy, and specifically kinetic energy. So the picture I've drawn, I'm back to my anvil example here of the person dropping the anvil, trying to drive the stake into a ground. Now, we're not going to worry about the person. We're just going to focus on the anvil for a moment. So imagine here, this is what I call position 1. And the anvil is a certain height here above the stake, basically. And in position 1, it's not moving yet, so its velocity is 0. Right, position 2, right, the anvil is falling, it's accelerating down under the influence of gravity, so the motion diagram might look something like this. Again, the dots are just representing the velocity of the anvil here. And position 2, imagine the anvil's just barely over the stake here. There's a little distance here. There's a little gap. You know, I really don't need that line right here. I'll get rid of this. Okay. Position 2, imagine the anvil's just barely over the stake, but there is a little gap there. And if we talk in terms of energy now, the potential energy at position 2 is much smaller than at position 1. The higher the anvil is dropped from the stake, the more potential it has to drive the stake in. So in position 2, the potential energy is very, very small, or it might even be 0. Now, it turns out that potential energy can be measured from any place that you want. So the actual numerical value at position 2 is not important right now. It could be 0, it might not, depending on where you measure it from. But the important thing to realize is that the potential energy at position 2 is a lot less than position 1 because there's very little height here above the stake. The anvil, however, still has the ability to drive that stake in. The anvil's moving. It's got a pretty reasonable velocity now in this direction. I would call that V2 for velocity in picture 2. And the velocity combined with the mass of this object gives this system the ability to drive that stake in. And that's a kinetic energy. Remember, kinetic energy is defined as, and I'm just going to shorthand this, energy due to motion. So the anvil, the speed of the anvil combined with its mass gives it the ability to drive the stake in. Now notice that there's kind of a conversion that's taking place. Here at position 1, there was no kinetic energy. The anvil wasn't moving yet, but it had a relatively high potential energy because of its location, its position above the ground. At position 2, it has a low potential energy, but a high kinetic energy. And it turns out that what has happened there is kind of a transformation of potential energy to kinetic energy. And I'm going to save that discussion for more upcoming videos. But anyway, position 1 has the ability to drive the stake in due to the position of the anvil. Therefore, position 1, we have a potential energy. When the anvil is at position 2, it's the motion, the speed of the anvil, combined with its mass that gives this anvil the ability to drive that stake in still. And that's what kinetic energy is. So, again, just to recap this video here, all systems need some sort of energy to do work. Remember, work is force times distance. So basically, all systems need some sort of energy to apply a force and push something, to move it. Energy comes in 2 main types here. We've got what's called potential energy, kinetic energy. Potential energy is energy due to position. Kinetic energy is energy due to motion. Now, oops, we don't need this. You'll hear terms of you'll hear other types of energy terms, like you might hear the term electrical energy, or you might hear potential energy, or I'm sorry, chemical energy or thermal energy. In reality, all energies can be related back to one of these two. So in the example of chemical energy, we'll talk a little bit about maybe gasoline. Gasoline is a substance that has a very, very high energy content stored. I mean, it's second really almost only to nuclear, I think, as far as how much energy you can store per pound. Lots of energy stored in a gallon of gasoline. That energy is effectively stored at the molecular level. Basically, when you combust the gasoline, big molecules break up, combine with oxygen and form smaller molecules. It's the molecular position with respect to one another that gives these large molecules their energy, and that's a potential energy because it's energy due to the position of the molecules, how they're attached together, how all the atoms are attached together. So really, in reality, there are only 2 types of energy, kinetic and potential. But we will use terms from time to time. You'll hear terms like thermal energy or chemical energy or electrical energy. But really, when you look at I guess not the big picture, the tiny picture, scaled all the way down to the atom, all energies can be thought of as either potential or kinetic. So anyway, I hope this video helped conceptually helped you understand what potential energy is, what kinetic energy is, what its role is as far as doing work. And I look forward to making more videos here illustrating examples of how to use energy concepts to solve problems. Have a great day.